Hello again, everyone. And in this section, 2.3, we're going to look at applications of linear equations, which unfortunately generally means word problems. And I know that scares a lot of people. I know for myself, word problems, I don't like them that much either. I like being given a formula, solve it. I don't like this whole reading and having to figure out what is it that they're trying to say. And that's usually where the largest difficulty comes from with word problems. It's understanding and figuring out what are they trying to say and what is it that are they asking for. Now, as you'll see both on the site, which I will link and annotate here, is a table of common phrases and what it is they mean. And many times, saying both the phrase out loud and the actual expression that it represents out loud is almost, you can see it. But to help you, and there's a table on the site, and there's also a table within the book in this chapter. What I've included here is a link to a little game called Math Expressions Millionaire, which is like, Who Wants to Be a Millionaire? Only instead of being general knowledge questions, it's all math expressions. And they take a math expression in word form. You have to match it with the actual expression that it relates to. It sounds simple, but of course, just like Millionaire, as you go through, it gets more complicated and more involved, and which makes this game a great way to review going from words to the math expressions themselves. The site is good. Also serves as, with the table, serves as a great review, but the game itself, because it changes all the time, you're not seeing the same thing every time like you do on the table. It just keeps changing, so it's very helpful to use the game as a review tool to figure out, just, do I understand it, and what problems and what type of words are you having problems with, that you can then take to me or to our message boards for your classmates to see other ways of maybe, how can I remember this and use this, so that way I'm not using it and getting it wrong again. So one example, of course, is just the phrase, twice a number decreased by 3 is 42. There's several cues here within this phrase that we're going to look at. Largely the word decreased by and is. The word is almost always the same as an equals, and of course decreased by is usually a minus. So we're going to look at this one little bit at a time. First, we're going to look at twice a number. If you consider just that, well, what is twice a number? Well, that's just 2 times x, where 2 is, of course, twice, and x is a number, some number. We don't know the number. It's the variable. It's something we just don't know. Now we're going to take that and we're going to decrease it, which is what the minus sign's for. So we decrease by, that cues you that this is a minus. 3, of course, is, 3. And that whatever this is equal, or is, 42. Now, all you have to do is take this and put it all together, and you get 2x minus 3 equals 42. We've just taken the word problem and we've converted it into a math expression. So now we're going to look at a real problem in which that involves perimeter and a rectangle. So we know that the length of a rectangle is 1 centimeter more than twice the width. And the perimeter is 110 centimeters. Find the length and width. So first we need to know, what do we know? First thing we're going to look at is, we're going to look at the first sentence. The length of the rectangle is 1 centimeter more than twice the width. So we know that length, we'll call L, is 1 centimeter more, is equal to 1 centimeter more than twice the width. So we have L equals 2W plus 1. In this case, if you wanted to go exactly as it's phrased, it would be L equals 1 plus 2W, but many times you want to have the variables as far to the left as possible and always whole numbers to the right. But this is the same thing because it is a plus. So, 1 plus 2W, 2W plus 1, it's the same thing. So now we know the length is twice the width. So now let's go to the next sentence. We know that the perimeter is 110 centimeters. Well, we all know what perimeter formula is. Its perimeter is twice the width plus twice the length. Because if you go all the way around, you go through the width twice and the length twice. So now we have this equation, and we know it equals 110, so we could just plug in 110 is perimeter. The width, we don't know what the width is yet. And technically we don't know what the length is either, but we do know that the length is 2W plus 1 from right here. So we just plug in 2W plus 1 right down here where L used to be. So instead of 2L, we have 2W plus 1. So now we have one equation, one variable, just W. This sounds like a linear equation in one variable, just like what we've been studying. Shocking, I know. So now we take this and we're just going to simplify it. Step 1, simplify both sides. Obviously 110 is as simple as it's going to get. So now we simplify the right side. So we distribute the 2. We get 4W plus 2 after simplifying. After distributing, we then combine 2W and 4W to give us 6W plus 2. Now, our next step, we need to isolate W on one side. It already is. So we need to get rid of the 2. So since this is plus 2, we need to do the opposite to get rid of it. So we're going to subtract 2 from both sides. So we get 108 is equal to just 6W. Now we want to divide. So now that we have a 6W, we need to divide both sides by 6 so we can get W all by itself. So these 6's will cancel out. And what we get is the width is 18. Now we need to be careful. We're not done. The question said find the length and width. We found the width. So now we need the length. Well, if you remember from earlier, from that first sentence, length is twice the width plus 1. So now we just plug in. Now that we know what W is, we can just plug it in. So we get 2 times 18 plus 1, which is of course 36 plus 1, but so 37. So our final answer is the length is 37 centimeters and the width is 18. Now make sure the answer, we can't just say the length is 37. That doesn't tell us anything. 37 what? Is it 37 meters, 37 kilometers, 37 miles? You always have to make sure with word problems, you need to make sure you use the right measure that describes the actual numbers. In this case, centimeters. Since everything here was talked about in centimeters, we need to make sure our answers are in centimeters as well. We're going to get a little more complicated now. So, in 2006, the total annual U.S. health expenditures were about $2,000 billion. That's the equivalent of $2 trillion. This is an increase of 180% over 1990. So what is the total expenditures in 1990? Well, I know your heads are spinning right now. So first we need to look at, okay, what did we know? First, we know that there was an increase of 180%. First, we need to convert that to a number. So first we're going to convert 180% to 1.8. And then what were total expenditures in 1990? Well, that's what we want, so why not just call that X? We'll say that's what we're looking for. That'll be our variable. So now, we know that X times whatever the change was from 1990 has to equal 2000, because 2000 is what it is now. Well, now, I say now, but in 2006. So now we have to look at what is change from 1990. Well, second sentence tells us this was an increase of 180% over 1990. So that means that the change from 1990 is 1.8 times X, which is 180% over 1990, which is X, because we don't know what that expenditure was in 1990. So now we finally converted this from an equation, from a whole word problem, into a linear equation in one variable. So now we can go back to our 5 steps and actually solve it. So we can simplify to 2.8x and divide both sides by 2.8, so we get x all by itself, and we get x is approximately 714, or in this case, $714 or billion dollars over in 1990. This one is also, you're going to find from your chemistry classes, it gets a little bit more involved, but it's not too bad. In this case, we're going to make a table to help us solve this equation. So first we look at, a chemist has to take 8 liters of a 40% acid solution. We're going to mix it with a 70% solution to get a final mix of 50% solution. So how much of the 70% solution should be used? Now, if you've already had chemistry, you might have seen some problems like this before. If you haven't, well, first we need to go label our variable. First we're going to say X, which is, X is the amount of the 70% solution to be used, which is what we're looking for. A lot of times using X, our variable be what we're looking for, is usually very helpful. 9 times out of 10, 99 times out of 100 even, that's going to be the best way to go. So we'll just say X is what we're looking for, in this case, the amount of this 70% solution. Now we're going to make a table that shows liters of both of these solutions and then a final solution. And the best way to say it is, we know we have 8 liters of one solution that is at 40% acid. So that means the amount of pure acid in this 8 liters is 40% of 8, or 3.2 liters. Now we have some solution of X. We don't know how much it is yet, but we know that it's a 70% solution. So the amount of acid in this must be 70% of X, or 0.70 times X. Now, after we take this and we mix it all together, we know that there'll be, 8 plus X, because we started off with 8, we added X amount of liters, so now we're at 8 plus X liters. 8 plus X equals 8 plus X. This solution is at 50%, So that means the amount of acid in this final mix is 0.5 times the total number of liters, 8 plus X. Now, the amount of total acid that we use throughout this whole thing has to be the same. So that means the amount of acid in this part, the amount of acid in this part, added together must be this part. So we're going to take this and add them together and make it equal to this. But in this case, so we have 3.2 plus 0.7x equals 0.5 times 8 plus x. So now we take our initial equation and we go through our steps. Step 1, simplify both sides. So obviously the left side is as simple as it's going to get. So we have 3.2 plus 0.7x. Here we distribute the 0.5. 0.5 times 8 is 4. 0.5 times x is, well, 0.5x. So now step 2, we need to isolate x to both sides, to one side, and get it all by itself. So in this next step, I'm actually going to combine step 2 and part of step 3. What I'm doing here is I am moving x so that way x is all on the left side, and I'm moving the 3.2 over to the right because I want x is all by itself on the left. So I'm doubling my steps in one step. So I'm taking the 3.2 and getting rid of it by subtracting 3.2 from both sides, here and here. And then, so that gets rid of this 32 from up above. Then I want to get rid of this 0.5x to move it to the left. So I'm subtracting 0.5 from both sides, seen here. So this simplifies down to 0.2x equals 0.8. So our final step is, of course, we want x all by itself, not just all the x's. We want it just one x. So we need to divide both sides by 0.2. So we get 0.8 divided by 0.2, which gives us 4. So x is 4 liters. In this case, x is our final solution. We need 4 liters of the 70% solution to get a full 50% solution. Again, please click on any of these links to jump back to and review and revisit any of the topics that were discussed today. If you have any questions, again, please post here in the comments on this YouTube video or on the site for this particular lesson. I will be checking both. The lessons site will be best because there's more available from your other classmates, and plus it's a lot easier to see. YouTube comments can get drowned out depending upon how many people post. So again, take your time, and I will see everybody in class next time.